We're going to look at concavity here, which is a description of the curviness, so to speak, of a function. So jumping into that, a function is considered to be concave up, or we also call that positive concavity, when the second derivative of x is greater than 0. So if the second derivative is greater than 0, if the rate of the rate is increasing, that's concave up. So the rate of change will become more, will increase over time. Or in other words, it's becoming more positive. And the way that you can kind of give yourself a reminder of it, it's something that will form, a smiley face, a smiling face. So this is an example of concave up behavior on a graph. You see that at all points, the point to the right has a more positive slope or a more positive derivative. So at the beginning here, we've got a very big negative derivative, but then that negative becomes less and less negative. Eventually, we reach a derivative value that's 0 or a rate of 0. And then our rate starts increasing, becoming more and more positive until it's a very steep positive over here. So through that whole motion, it's becoming more positive. That is why it is concave up, and that's why the second derivative is greater than 0. Or rather, the fact that the second derivative is greater than 0 produces that behavior. Concave down is exactly the opposite. So a function is considered to be concave down or to have negative concavity when the second derivative is less than 0. So in other words, the rate of change of the function becomes more negative. The rate of change will become or will decrease over time, which can also be written as become more negative. Now, the become more negative, become more positive is my preferred way of doing it as someone coming from kind of a physics or applied math background, because I tend to think of the absolute value being whether we talk about something getting bigger or smaller. But in mathematical terms, big negative numbers are, or large magnitude negative numbers are smaller than small magnitude negative numbers. If that doesn't track, don't worry, just stick kind of with the math here. So negative concavity is a frowny face, and just like with the positive concavity, we can see that we start with a very big positive slope, very big positive rate of change. As time goes on, that positive becomes smaller and smaller, closer to 0. Eventually, we see 0 rate of change. Then we see a little bit of negative, more and more and more and more negative. So over time, we go from a lot of positive to a lot of negative. In the middle, we have less positive, 0, less negative. So that's concavity. And we can see that here. We can see kind of the interface of increasing and decreasing behavior as well as concavity. So kind of this left side of a smiley face is when we are decreasing but concave up. When we are increasing and concave up, we have the kind of upturn of the smiley face. When we're increasing but concave down, we get this kind of left side of a frowning face. And when we're decreasing and concave down, we get this downward smiley face bit. So what's interesting to note is that when these are opposite signs, so when one is positive and the other is negative, the slope will eventually become flat. When they're the same, the slope will eventually become infinity, or technically negative infinity. So opposite signs meaning our slope gets more flat over time. Same signs means our slope gets more steep over time. And that will always be the case. So lastly, we're going to mention inflection points. And inflection points are locations where the concavity changes. These will always occur where f, the second derivative of f of x, is equal to 0 or undefined. But like critical points, not all of these points are inflection points. So these will identify the places you might have an inflection point, but you have to actually check, did it change signs on either side? And so that's what we have for concavity.